Hello again. In this new video, we are going to see a better way to write our simple program that reads one pin of the input port and sets one pin in an output port. We are going to see a more convenient way to write this program, okay? So we have used so far the load and store instructions and logic instructions to manipulate individual bits, but the AVR microcontrollers are very powerful in this respect. They include these instructions here, these instructions here, the set bit of an input-output register and the clear bit of an input-output register. It means that we have instructions to set or clear individual bits in the registers. Okay, so we don't need to read the whole port and then change one bit and save the whole port again. We can directly change the bits in the ports. Okay, but before that, there's something important that we have to understand, is that we here in our ports, in our ports, I have said in a previous video, they have an address in memory. For example, port B have an address in memory which is 25, okay, in hexadecimal. But the ports also have an address in the input-output bus, because you can access those ports by using memory instructions that transfer data to memory, or instructions that transfer data directly to input-output ports. Okay, these are the in and out instructions. And for in and out instructions, the address is a bit different because these addresses are independent, so they are a different number. Okay, in the AVR, in most AVR chips, the input-output address is 32 less than the memory address. Okay, 32 in hexadecimal is 20. That's why if the address in memory is 25, the address in the input-output bus is only 5, and so on. Okay. So when we manipulate the bits in the ports, we have to use they use the input-output address and not the memory address. Okay, so we will see how to do that. Okay, so first of all, in this case we are going in these 3 lines of code. We want to clear the bit 7 in DDRD. Okay, so to do that, we don't need that many instructions. We can use the clear bit in input port, okay, in input output port, and we put the DDRD and we say the bit we want to clear. Okay, the bit we want to clear is bit number 7. Okay, so with this instruction we can really eliminate all that. Okay, again, it's not that bad, because in case we want to set more than one bit, for example, if we want to set 4 bits to 0 or 5 bits, it may be better to do it like that. Okay, because this way we set all the bits at the same time. But if we just want to activate one bit, we can do it like that. Okay, so we can do in one single instruction what we do in 3 instructions. Okay, we clear the bit in the input-output port directly. We don't need to read it, change the value, and write it again. Okay, that's great, but this is a small problem here, is that this DDRD, let's see it here. Okay, let's see it here. Oh, I'm sorry. Okay, this number is, this number is to DDRD is 2A, okay? 2A is the address in memory, but it is not the address in the input-output bus. In the input-output bus, the address is 0A. So we have small problem here because we can leave our code like this, okay? Because DDRD is actually a 2A, but we need the address of the in the input-output bus, which is 0A, okay? So we need to convert from the memory address to the input-output address. It's just subtracting this number, okay, number 20, okay? We can do it manually, but the preprocessor already has a function to do that. The name of the function is a bit clumsy because it's SFR IO ADDR. So this is a preprocessor function, let's say, okay, that will take the address of any peripheral and we convert that memory address to input-output address. So whenever we want to access a peripheral through the input-output bus and not through the memory bus, we need to prepend this macro function, okay? It's a bit big, but this is the way it's defined in the AVR library. So this will be the way to do it. And here it is the same. If we want to activate this one, we could set bit in input-output port, okay? We will say SFR IO ADDR port D. This is to activate the pull-up, and that's it, okay? This instruction will activate the pull-up for us. You see, we are saving lots of instructions there, and the same thing here. Okay. Now here, saying we can set bit input output here, and it will be IO DDRB to make it an output port, and we want to set bit number 5, so we'll put here bit number 5. Here we will put bit number 7, okay, and we can remove all that. Okay, so now actually using these names, these numbers here, this is not a good style of coding. You know, never use constants directly, because in the future those constants may have to be redefined, okay, somehow. So the standard definitions already have defined names for the pins in the ports. So we may use PD7 here and PD7 here. This is actually the same because PD7 is equal to 7, PB from port B5 is equal to 5, but it makes, supposedly, it makes code more clear, but using these things here, okay? Okay, now, same thing to read and save. Here we are reading ports, saving ports. We basically are checking if one of the pins is equal to 1. So again, the AVR has branch instructions that can check individual bits in the input-output ports. So let's go back to the branch, or let's go up to the branch instructions, and we have these instructions here, okay? The escape if bit in input-output register is cleared, or escape if the bit is set, okay? And we put the input-output register and the bit number we want to check. So basically it means that we can remove everything we have here. And we can use escape if bit in input-output register, just to make it similar, is set. Okay, this instruction will skip. Skip will mean that it will skip the next instruction. So if the bit is set in PD7, we skip the branch to E0 and then we continue here. So we cannot jump to anywhere we want. We just can skip one instruction, but it's not a problem because we can skip the next instruction and then here we branch to whenever we like. So it may be a little bit confusing, but just if you skip if set, then in 2 instructions below you do whatever you want to do when it's set, when it's 1. So skip if bit is set. Which bit? The bit in pin D. Okay, so we will use the macro. We'll copy from here the PD7. So if in the input register of port D, the pin D7 is set, we skip these instructions, we go here. So here what we do is that we activate the output. Okay, to activate the output, it is set bit input output register of port B, register of pin number 5 or bit number 5. Okay, and go to continue. If not, we basically do the same. We copy this instruction, but not set. We want to clear that bit. Okay, so you see it is much powerful than before. Okay, so we can put a comment here. Okay, so the program is greatly simplified. We can save it, and now we can repeat everything. Okay, we will move to our terminal. Here we'll go back. Okay, we recover the comments. We compile, assemble the command, the program. It's amazing that we don't have mistakes. I'm being very careful. And now what options we have? If we have a board, we can test it in a board directly, okay? But we can debug it as we have done in the previous video. So I still have the terminal here, so you can go to the repository, okay? And you can check the debug instructions, the debug commands if you want them. But if you have just done it, it's simple because you have it in your remembered by your terminal. So we first execute the simulator. Okay, the simulator is already running the program. Now in the other, oh, not that big. In the other terminal, we execute the debugger. We execute the initial configuration. Okay, we connect to the simulator. We enable the terminal user interface. I will put the configuration alike. Okay, and now we just step through the program. Okay, we step again. Okay, and now we are at the beginning of my program, and we can configure the display. Again, we are interested in checking many things. Okay, so we want to display DDRD to see if we are configured it correctly. Pin D to see the input bit. DDRB to see the output port configuration, and port B to check the output value. Okay, and we just can step now through the program again. Okay, we have activated the pull up here, so the pin D gets active. Everything works fine. Now the input is 1, pin D7 is 1, so at some point the port B output will be 1. Okay, Oh, it's set to 0 in the end. Remote jump continue. Set bit, port B set to bit. Oh yeah, it's not working fine because you see, we have set port B, but we are missed one instruction we had before that we don't need now, the STS. We are storing R17 in port B. We are not using R17 now. So by doing so, we are setting port B to 0. Okay, I have just realized because we are debugging the code, so we expect to see something, we see something different. Okay, now the point is that we have to change the code, so there's no option but to stop everything. We stop the simulator here, we stop the debugger. Okay, interrupt. And okay, I don't think if we can continue like there if I recompile the program, so I will better get out of the debugger. Great, and let's modify the code. So basically this line that we don't need anymore, we save the code, let's repeat, assemble the program again, execute the simulation again, execute the debugger again, and do all the initialization again. It may be a bit not very nice to do it once and again. Okay, so there's an option for the debugger. I'm going to stop it. It will quit the debugger. Great. You can tell the debugger to execute some commands when it starts debugging. Okay, so you see that what we have done, I'm going to create a new file here. I'm going to, and in this file, I'm going to put the commands that we are executing at the start, when we start our debugger. Okay, so we are doing this all the time. Okay, we are connecting to the simulator. Then we are enabling the the graphical interface. Okay, but what we are going to do is we are going to put a breakpoint in function main at the starting of our program, because normally we have to step a few instructions until we reach the starting of our real program. We are going to do it automatically. We want our debugger to set the breakpoint at the main function, which is where our program starts, and continue, okay, to that point. When we are at that point, we want our debugger to print some useful data. We want to display DDRD, we want to display PIND, we want to display DDRB, we want to display port B. So what we are doing is we are writing in a text file all the commands that we want our debugger to execute whenever we run the debugger, so we can save having to execute everything every time we run the debugger. Okay, we are going to save that program. We are going to save it as gdb.conf, for example. Okay, and now when we run our debugger, we can tell our debugger to run those commands for us. Okay, I don't think I remember the instructions. So AVR gdb --help will give us what option we can use to read initialization programs. I think it should be like here somewhere. Yes, it's command equal or -x. Okay, execute gdb commands from file. Okay, so we can use the short version, which is -x. So this time we are going to do avr -x gdb.conf. Okay, so now our debugger will execute all this, and we at the end of that, the program is ready to be debugged, hopefully. Okay, if we haven't made any mistakes. So let's execute that. And that's it. Okay, I have missed to enter the terminal user interface. We can do it now to enable. Okay, and here we are, and we can add it to my set of comments for next time to enable for the next time I run the debugger. If you don't like the format, you can change the way it's displayed to your preferred way. And I don't know how to do it automatically, but that's an improvement. And now just a step. You see all the interesting registers are printed. So we go with step, pin D is 1. So port B is set to, port B5 is set to 1. Okay. If we set pin D equal to 0, and then we step again at some point when it's checked, the value is checked, branch oh, it's not working again because we have left the branch instruction here. We skip if bit is set, okay? And we said before branch if equal branch eq, which means branch if 0, but we are not doing any AND operations. So if bit is set, we go here. It's not 0. If the bit is not set, we want to go here directly. We want to jump conditionally, okay? So it's not a conditional branch again. So it's another mistake. Believe me, it was not prepared, okay? It's only this afternoon. I'm not very good at programming. So we stop everything, Control-C, quit, okay, modify our code again. This is an R jump now, okay? If it's 1, we go here and activate the output, and then we continue. If it's 0, if it's not 1, then we jump to is 0 and do this, okay? It may be rewritten in some other way, okay? But it's not that bad, like that. So let's go again, compile the code, run the simulator, start the debugger. Okay, now the debugger goes right into graphical mode. And we don't really need to activate the register this time. Just let's step through the code because we already have displayed here everything that is interesting. Okay, so this way the output is 1 now. We set pin D equal to 0, and then we step again. And at this point, okay, the output is set to 0. Okay, so that's it. Now the program works correctly. Now with this, we have simply a better version of our program using proper input and output checking instructions and these skip bit instructions, and using the symbols for the names of the ports and for the bits in the ports in a more sensible way. Okay, so that's all. Thank you.